but let us see what happens. So y star x plus f of x bar minus y star x bar, this is this, greater than or equal to all this right-hand side. For every x. Rearranging terms, we get g of x on the left greater than or equal to g of x bar on the right. F of x bar and f of x bar cancel out, and then I get plus y star minus x star, no, x star minus y star, x minus x bar. Okay? Here I have x star x minus x bar, which is here, and here I have y star x minus y star x bar, which moves to the right-hand side with a minus sign. So this is what I get. And this holds for every x. So what's the conclusion? That x star minus y star is a subgradient of g at x bar. Thank you. Yes. Yes. Then, so we have x star minus y star belonging to the subdifferential of g at x bar. So the conclusion is that x star, which is of course equal to y star plus x star minus y star, belongs to the sum of the subdifferential, because this is in the subdifferential of f and this is in the subdifferential of g. So we have succeeded to decompose an arbitrary element in the subdifferential of the sum as the sum of two subgradients. One a subgradient of f and the other a subgradient of g. Okay? Okay. Okay. As I said, we have to be careful. And yesterday I did something which was completely correct, but it should not be evident that it was completely correct. So let us justify now this step. So yesterday, one of the things we saw is that if the subdifferential contains just one element, then the function is differentiable. The argument was extremely simple, but I will repeat it now, and you will tell me if you see any problem. I mean, it was correct, but maybe it's not evident that it was correct. So the argument was, okay, suppose this is a singleton, implies f is differentiable at x bar. This was the statement. And the argument was, if this is a singleton, say the singleton of x star, then because the relation we saw between directional derivatives and subgradients, then I said f prime of x bar d is equal x star d. So the directional derivative, I said, is linear in D. So the function is so-called Gateau differentiable, and I mentioned that for convex functions, Gateau and classical or Frechet differentiability are equivalent. End of the proof. Do you see any problem with this proof? The proof is fully correct, but there is a step which requires some justification. Do you see any problem? No? The problem is that I was mixing contexts. We are in convex analysis, and I was using a result of classical analysis about Gateau differentiability. And what's the problem? The problem is that in convex analysis, this is the one-sided directional derivative. And in classical analysis, this is the two-sided directional derivative. So concluding that the one-sided directional derivative is linear in the direction does not, in principle, allow me to get the conclusion. But in fact, it's very easy to see, and I'll try to convince you, that if the one-sided directional derivative depends linearly on the direction d, then it's two-sided. It's the two-sided derivative. So this is the limit as t goes to 0 plus of x bar plus td minus f of x bar divided by t. And what I'm going to prove, can be left as an exercise in fact, is that under this situation, the limit is actually the limit as t goes to 0, not just 0 plus. So to the same, I simply have to consider the limit as t goes to 0 from the left. And see that it coincides with the limit from the right. Okay? So let's make an obvious change of variable. S equal minus t. So this is limit as s goes to 0 plus of f of x bar plus s times minus d. Okay, I'm replacing t with minus x. Minus f of x bar divided by minus s. Okay? This minus, of course, comes out. And because now s goes to 0 from the right, this is our one-sided directional derivative in the direction minus d. But we are assuming linearity. So this is minus x star minus d, which is of course x star d, and x star d was the one-sided directional derivative. I mean, it was the limit as t went to 0 plus. So the limit from the left is equal to the limit from the right, so the limit exists. The derivative exists as a two-sided directional derivative. It's only after making this simple observation that I have the right to say the function is Gateau differentiable. You missed that detail. I missed it too. But later on, when I was in my room, I thought, we are dealing with one-sided directional derivatives. Well, you yesterday asked me about the subdifferential of absolute value of x plus y. And my response was it can be computed from the definition. And this is true, but this is not the most efficient way. There is another calculus rule, which I'm not going to prove, but I'm going to use, which deals with compositions of convex functions with linear mappings. I will tell you this calculus rule, and then we will apply this to your function. Okay? So the situation is the following. Suppose we have a linear mapping from Rn into Rn, linear. And we have a function f from Rm into the extended reals. And a point x bar in the domain of the composition. What can we say about the subdifferential of the composition at x bar? Then what can be proved in general without convexity is that it contains A star. A star means the adjoint operator. If you think in terms of matrices, the transpose matrix. Okay, if you look at A as a matrix, then A star would be represented by the transpose. Of the subdifferential of F, at Ax bar. This is an exercise as simple as the one we made for the sum. Suppose I have an element y star in this subdifferential. and take x in Rn, then f composed with A at x is f of Ax bar, no, f of Ax, which is greater than or equal to f of Ax bar plus this element is a subgradient here, for every y in Rn. Well, no, I don't like this, because I have too many variables. I have x here and y here. So what I do here, I mean, the definition of gradient, the fact that y star is a subgradient of f at A of x bar simply says that f of y is greater than or equal to f of x bar plus y star y minus Ax bar for every y. Okay? But this is the subgradient inequality. But now I am applying this to Ax. Okay? So here I should write Ax. Okay? And of course this is f A of x bar plus A star. I mean, A moves to the first factor as the transpose, as the adjoint operator. Okay? Plus A star times x minus x bar. A star, y star. And this proves that A star, y star is a subgradient of the composition at x bar. I didn't use any convexity. This is very simple algebra. But if we impose some extra condition, namely that the range of A intersects the interior of the domain of F, then we have equality here. Okay? I'm not going to prove this, but it's true. Then with this formula, we can already compute your subdifferential. So your function was g of xy equal absolute value of x plus y. Okay? Then it can be expressed as a composition of that type. So G is f composed with A f being the absolute value function Well, the notation here is a little bit unpleasant because maybe it's better to use x1, x2. Okay? Then f of y equals the absolute value of y, and A is the linear mapping which assigns to x1, x2 the sum. Okay? Do you agree that G is the composition of F with A? Then, you were interested in the subdifferential of G at some point. Okay? Then, this is the subdifferential of F composed with A at x bar 1, x bar 2. And we can apply this formula because the range of A intersects the interior of the domain of F, because the domain of F is the whole real line. So the interior is the whole real line. Okay, so then I can say that this is A star, the subdifferential of F at A of x1, x2 bar. This is the particular case of the general formula in this situation. But what is A transpose? A in this case, let us use now matrix notation. A is the row vector 1, 1. Then A transpose is the column vector 1, 1. And A of x bar 1, x bar 2 is x bar 1 plus x bar 2. So now I simply have to compute the subdifferential of F, which is the absolute value function at a point x bar 1 plus x bar 2. So this subdifferential we know that it reduces to -1 if x bar 1 plus x bar 2 is negative. I mean, the subdifferential of the absolute value function is the sine function defined at 0 as the interval -1, 1. Okay? Then it is -1, 1 if this sum is 0. And it is the singleton of 1 if the sum is positive. Then plugging this into here, we obtain that the subdifferential of G at x bar 1, x bar 2 is 1, 1 times the set minus 1. If the sum is negative. Then the product of this vector with all numbers between minus 1 and 1. You can express it in many different ways. It's the segment joining the points minus 1, and 1, 1. Okay? So if you want the convex hull, the smallest convex set, which is the segment, that contains minus 1, and 1, 1. If the sum is 0. And 1, 1, the vector 1, 1, if the sum is positive. Okay? So this formula is very useful. One can compute the subdifferential directly, but one has to work much more. Okay, it's not so evident. Okay? Thank you for suggesting this problem, because I was not planning to give this formula, but in fact it's an important formula, no? Because this situation of composing a convex function with a linear function appears very frequently. Any questions so far? Suppose f is convex, and x bar is a point in the interior of each domain. Okay? Then we saw that for every direction D, the directional derivative at x bar in the direction D is equal to the maximum over x star in the subdifferential of the inner product x star D. Okay? So this formula says that if you give me the subdifferential at x bar, I can compute the directional derivative. So it expresses the directional derivative in terms of the subdifferential. Is there any expression which does it otherwise? I mean, is there a way to express the subdifferential in terms of the directional derivative? So here you give me the subdifferential and I compute the directional derivative. My question is, if I give you the directional derivative, can you compute the subdifferential? Let us see. If X star is a subgradient, then because of this equality, which we already know, X star D is less than or equal to the maximum, which is the directional derivative. This means that the subdifferential is contained in the set of X star such that X star D is less than or equal to F prime X bar D for every D. I'm doing all this because I didn't introduce the so-called Hormander duality between closed convex sets and sublinear functions. If I had given that theory, everything will be simpler, but in fact it's going to be very simple still. So do you agree with this inclusion? But I claim that equality holds. So suppose X star is an element in the right-hand side of this inclusion. I have to prove that then X star is a subgradient. Okay? But then let's prove the subgradient inequality. I consider any X in the space, and for this X, I use this inequality with D equal X minus X bar. And now, an important fact is that we proved that for convex functions, the one-sided directional derivative is an infimum. So this is the infimum over T positive of Fx bar plus T X minus X bar minus F of X bar divided by T. So is less than or equal to this expression for any T. I choose T equal 1. And then I get F of X minus F of X bar. So I exactly obtain the subgradient inequality. So this shows that X star is a subgradient. So we have equality here. No? Every element in the right-hand side is a subgradient. We have equality. Now I want you to pay attention, to compare what we have obtained with the definition of subgradient. So let me write the two expressions here for better comparison. The definition of subgradient was the one we have written 1 million times already. And now what we have seen is that if our point is in the interior of the domain, X star is a subgradient if and only if X star D is less than or equal to f prime of xd for every d. We have the definition of subdifferential, we have a characterization of subgradient. Do you observe anything interesting here? The first equivalence is for any function. The second one is only for convex functions on the interior of their domain. The definition of subdifferential is global. You need to know f of x for every x in the space. Local information is not enough to obtain the subdifferential. But if your function is convex and you are in the interior of the domain, I just need the directional derivative at x bar, which only requires local information. Okay? So in particular, I told you yesterday that the subdifferential of a non-convex function is useful, in particular when dealing with DC functions, differences of convex functions. But then it's a global notion. Local information is not enough to have the subdifferential. But when we are with convex functions on the interior of the domain, just knowing the directional derivative, which only requires local information at x bar, it gives you full information about the subdifferential. Okay. Now, where is it? I lost something, but it's not a problem. This is 11, 12, 13. Ah, yes, here it is. You want to stop now? Yeah. So one thing is still to be seen is the integration result. That if two functions have the same subdifferential everywhere, then they are the same up to an additive constant. The proof in Rockefeller is complicated. I will give you two proofs. One which is extremely simple and came out after I was yesterday discussing with Devdas. And we will see why that simple proof is not in Rockefeller's book. Okay? And then I will give you another proof which is not so short, but is much more elementary. Okay? So this is what we will see after the break. Thank you.